Hello, you guys. My name is Onur Shen, and I'm a master's student in Özyeğin University, which is located in Istanbul. And it's my fourth year now due to the pandemic, but throughout the whole my master's, I have learned a lot about CFD. So today I will be teaching you the process of transient flows and how to acquire data and the mandatory statistical calculations to determine whether you have what kind of turbulence you have and whatnot. So today's topic will be transient flow and a flow over a Cape sphere utilizing large eddy simulation and dynamic fluid body interaction. So first of all, I will go through this presentation and tell you what large eddy simulation is about and what dynamic fluid body interaction is. Let's go. So large eddy simulation does not solve Reynolds average Navier-Stokes equations called Durant's equations. Durant's equations are full models, meaning that the whole flow is fully modeled. And there's statistical averages, so you don't have instantaneous velocity fields. You have mean velocity fields, for example, or mean pressure, temperature fields. Any property will have its mean value. And so large eddy simulation is not a random simulation. Instead, it's part direct numerical simulation called DNS and part model. And usually, depending on your mesh, of course, usually 80% of the flow is solved directly, while the remaining 20% is modeled. This means that the large eddies, like its name, it's a large eddy simulation, large eddies are resolved, and large eddies have the majority of the energy. So they produce the energy in the turbulence. So these take about 80% of the flow, and the remaining 20% is modeled by using subscript scale models. And this is done by using filtering techniques. And there's an actual equation, just like Reynolds decomposition, there's a decomposition. And in this decomposition, there's a filtering technique. And this usually, the filtering is usually a result of your mesh. So depending on your mesh size, the amount that will be resolved will change. So if you have fine mesh, you will be solving pretty much everything. If you have a coarse mesh, you will be solving less than the fine mesh. So large eddy simulation is very sensitive to your mesh size, the cell sizes, and whatnot. So again, the mesh itself can be considered as a filter as it determines the minimum resolved eddy size. For example, you have 4 millimeter mesh size, your cell size. And up until like 4 millimeters, it will resolve the eddies. But after the 4 millimeters, meaning like the eddies that are smaller in size will be solved by the model. So yeah, it's a part model, it's a part direct numerical simulation, depending on your mesh size. So the advantage of large eddy simulation over direct numerical simulation and RANs. So compared to direct numerical simulation, it has lower computational costs since you don't have to fully resolve every eddy, so the smaller size dissipative eddies. So remember the energy cascade. So there are the large eddies producing the energy, and there are the dissipative, the smaller eddies that are dissipating the energy. So these eddies can be small as like micrometers. So like if you have to mesh, if you have to like generate a mesh fine enough, you will end up with millions or perhaps billions of meshes. So instead of resolving these small scale eddies, the large eddy simulation models these, hence you save your computational energy. So it gives you a balance between direct numerical simulation and the Reynolds average Navier-Stokes. Well, however, compared to RANS, obviously it has more computational costs as it involves direct numerical simulation, yet it can show transient behavior of the flow. Like I said, the Reynolds average and Navier-Stokes equations, they do not show, I mean, they can show transient behavior, yet not as fine as large eddy simulation, since RANS is all about averaging through time. And also, large eddy simulation shows the interaction of eddies and energies transferred in the flow, which is again great for determining the transient behavior of the flow. And it's great for highly unsteady flows with varying boundary conditions, which we will have in this tutorial. And there are a few examples such as combustion and multi-phase reacting flows with mixing of layers and phases. And on the right-hand side, you can actually see the differences between RANS, LET, and DNS. As you can see, there's a mean flow field in RANS, while LET is more unsteady. So, like I said, it's 80% direct numerical simulation, depending on your mesh size, and 20% is the model. So, comparing LES with DNS, you can see how DNS can resolve defined scale in the flow, yet less just models them. So it's more smoother flow. Yeah. So I actually worked with multi-phase flows with large eddy simulation, and I can say that that compared with experimental data and numerical data I got from volume of fluid method and large eddy simulation, they're pretty close. I mean, not exactly the same, obviously, due to like the mesh constraints and whatnot, but the results are pretty close to each other. Okay, so in this simulation, in this tutorial, we'll be using coupled solver. And if you ask why, I'll go through it. So segregated solver, as it's in the name, is segregated, meaning that pressure and velocity equations are decoupled. So how this works is that you initially give a velocity and pressure field, then the algorithm, which is the simple algorithm as you can see on the right hand side, updates the pressure field, then corrects the velocity field. It's in a loop, pretty much infinite loop. So the velocity field is corrected, then updates the velocity field, then the pressure field is corrected. So it's a loop. And it depends iteratively correcting the pressure field and hence the velocity field. However, coupled solver is all simultaneously solve pressure and velocity properties and gives accurate predictions in highly chaotic flows due to this coupling. So there's a strong coupling between the pressure and velocity equations. Hence, it gives more accurate results. Yet it can be, I mean, it depends again on your mesh and like your solver values, such as the time step and all those. I mean, it can be compared to segregated solvers. Coupled solver can be computation demanding, since it solves everything simultaneously. So generally, coupled solver is preferred for its performance in transient simulations. And yet, if you have a big domain with like millions of meshes, you might prefer to work with segregated solver as it's faster. You can see on the right hand side how the segregated and coupled algorithms work. And one another important factor in these solvers is the discretization. And in this tutorial, we will be using hybrid discretization, which involves central and upwind discretization methods. So central is the more accurate yet more dissipative discretization method, and it's unstable compared to like upwind. Yet upwind is more stable, yet more prone to be to have errors and less accurate and forth. So there's a balance between these two. If you would like a more steady simulation, you would like to be more towards upwind discretization, while if you want more accuracy, yet there will be less stability. You will be more towards central. So this hybrid discretization is between 0 and 1. You can set the value. So 0 means central, 1 means upwind. So the default value will be 0.15. We'll be playing with that and we'll just increase it to 0.3 for more stability. Okay. So let's go to DFBI, which is dynamic fluid body interaction. It allows the body to deform or move while interacting with the fluid. So it can be translation, rotation, and in total there will be 6 degrees of freedom. And you can actually simulate fluid structure interaction, FSI, with this motion method. And in this method, in FSI, there's actually a fluid and a solid that is interacting with each other. So I'll give you an example on the right-hand side. There's a diaphragm. This is the motion of a diaphragm pump. And it's not perfect. It was my undergraduate project. However, there are 2 inlets and outlets. I mean, there are pressure outlets acting as inlet and pressure outlets. And so the rubber above, it's a rubber, and it goes up and down. So this is called FSI. The rubber has its own stresses while the fluid has its own stresses. For the rubber, you have to use finite element method, while in the fluid we use finite volume method. So these are all coupled. So okay, on the left-hand side of this, on the video, you can see the stresses on the rubber. While below, you can see the velocity and the pressure happening in the flow. All right, you can see the motion. Again, it's not perfect, but you can get the idea. This is called fluid structure interaction. Again, now the rubber moves up, moves down, pumping the fluid, which is simulating a caved sphere. I'll show you the topology and the geometry. It will look something like this from the top view. You can see on the left-hand side, and on the right-hand side, it's pretty much a very amateur drawing of this field, of this topology. So we will have an air domain, an overset domain, and overset domain for the motion, and the volumetric meshing volume, and you can see that in the orange. We need that so we don't have to create a fine mesh around the whole domain, just the specific area. So the objective of this tutorial will be teaching you how to acquire data and statistics properly. For example, velocity data as Excel files. You can export these automatically from STAR-CCM. And we can monitor data using sliding sample window. And we have to use sliding sample window as this simulation is very transient. And what sliding sample window means is that, let's say you have a simulation that is running for 1 second, okay? Instead of taking statistics over all 1 second, we can take statistics in intervals such as 0.1 seconds. Since this guy will be flapping through time, we can't just get mean values over all physical time, over all 1 second. So it makes more sense to take it in packets. And we will be doing that. So monitoring data, for example, variances, covariances, mean velocity field, mean vorticity, helicity, and all that. And you can see the transient inlet condition. It's an addition of, it's an addition of sine wave. So it gives a Fourier wave pretty much. And I'll teach you how to create this field function. Also, again, I'll be teaching you about the DFBI motion, how to set it up. And we'll be optimizing solvers for stability and accurate results. You will be creating field functions, parameters, and setting up scenes with these field functions. And I will also teach you how to use Java macro. And this is really useful while creating turbulence field functions, because it takes a lot of time and you don't have to do these all over again for other simulations. So you'll just set up the field functions and your region. The only thing you have to change is your regions in the part values if you have other simulations. And it's very useful. I mean, hopefully it will work for you as well. So yeah, that's the end of the slideshow. Okay, now we can go to STAR-CCM. Open it up, a new simulation. I have 6 cores, and you can check this out in your dxdiag command. Okay. Well, you can check how many CPUs do you have. So I have 12 CPUs that I have has 6 virtual CPUs. So I have actually 6 physical CPUs. So I'll just plug in 6 there. And you can check out your display. I have an NVIDIA so GTX 1070. You can check out your computer, your system properties here. So my memory is around 16 gigs, and it's recommended if you have 16 gigs, but this simulation won't be that computationally expensive. But anyway, you can always reduce your mesh. Okay, let's exit that. You have to have a power on demand key, obviously, so you just click these two and hit OK. I have opened my simulation, so let's save this guy. All right, you can save it anywhere. So I have named this beforehand, but we can just name it as Cape Sphere tutorial file 2, let's say. Okay, save it. And so we'll start with the 3D CAD. Say new. Right click, say new. Okay. So you can pretty much start anywhere you like, but for this simulation, to not confuse anything, I'll start at XY. I recommend you to start at XY as well. You can either create a sketch here or just right click on one of the planes and create sketch. And one of the first things we'll do is that we'll change our grid and make grid spacing 5 millimeters and number of fine grid divisions to 10. So this means that this one grid will be 5 millimeters and it will be divided to 10 pieces. So you can see the smaller sections, right? Okay, first let's start with our sphere. And this guy will have a radius of 0.05. Okay, there we go. And then we have to revolve this around. So what we have to do is do this and then trim the sketch. So we don't need these. Just leave that as a construction line. Okay. Oops. Sorry, I quit the sketch. So this small guy here will be our construction line, and this construction line will be used to revolve our sphere. Hit OK. Rename it sphere sketch. Okay, we can now revolve it. 360, and we don't want it to be merging with other bodies. Okay, you can actually specify which axis type you like. You can specify it. We have a construction line, so we'll use that. And you can specify a reference axis, but we have a construction line, so it doesn't matter. So hit OK, and then we will have our sphere. Rename it to sphere. Okay. Now let's create our cape, right? And again, we'll be starting at XY plane. And for this, we'll be using spline, but first, the length of the cape will be 37 centimeters. Okay. And then, so you would like the cape and the sphere to be merging. So to have a fine merge operation, we'll just start from the middle of the sphere and we'll create something symmetric, something like around like this, and end here. And you can actually control these. Something like that. Here, and then have one here around there. So that's approximately what that is. Delete this line, or you can just leave it as a construction. Your choice. Let's leave it as a construction line. Maybe we might need it. Hit OK. So now this, okay, let's rename it first. Cape sketch. So this doesn't have a thickness right now, right? So once we extrude it, it will become a sheet body, and we will witness that in a second. So extrude it, and instead of extruding for, oh wait, it has to be symmetric. So from the middle, it will be symmetric, and both sides will be 5 centimeters. But here's the problem with this. If you take a look here from above, you can see that there's a small amount protruding out of the sphere, and this will be a big problem while generating our mesh, okay? So rename it. So instead of like extruding the exact amount of the diameter of the sphere, just make it smaller, around 4 centimeters, 4.95 centimeters, okay. So update it, update your CAD. Now if you take a look, it's a fine, like I know there's a like small place there, but it's fine. So it's a fine, what do you call it? It's a fine merge. You can even make it smaller if you like even like this much. Update. So yeah. So now we'll give our cape a thickness. First, save your simulation. Okay. We'll give it a thickness. So right click, and we would like it to be symmetric in both directions. Make it 2 millimeters. So yeah. So there we go. I mean, 2 millimeters. Why 2 millimeters? Because in the mesh, we will have a minimum surface value, and we'll set it as 1 millimeter. We don't want it to be like super fine, just to save from cell number. So 2 millimeters, and our minimum cell size will be around 1 millimeter, so it can actually mesh it. Okay. Save it again. Now you have to merge these two. Merge sphere with the cape. Boolean unite. Stay precise. Yes. Now there's a problem with this as well. So you know how the cape comes here, and then there's suddenly a sphere, a very steep slope, and the prism layer will struggle generating mesh here. So to have a proper mesh around here, you select these two, okay, and we'll give it a fillet right here, create a fillet, okay. So the radius will be around 2 millimeters, let's say, or even we can make it better, 4 millimeters. Try it, 10 millimeters. Yeah, sure, why not, right? So now we have a very smooth transition here. Okay, the prism layer mesh can generate a mesh pretty finely. We can also like create a fillet here. I'm just improvising here, by the way, but it might end up bad, but let's see. Let's make it 1 millimeter. Two millimeters. I think that's a bit too much. No, it's fine. Yeah, make it 2 millimeters. It's okay. There we go. You have a fine transition here now. Okay. This is purely for generating the mesh, okay? All right, so we have the sphere. Now, let's draw our overset region. Create the sketch, normalize it, and we'll begin by sketching the front side of the overset, and we'll make a bullet shape. So from the middle of the sphere, our line will be 20 centimeters, okay? And for the back, this will be around 50. And the thickness or the width will be around 0.15, right? And we'll make this a construction line and apply a length dimension for parametric study. Maybe the overset region is smaller or bigger than you expect. So instead of going back to the CAD, you can just change the values from the simulation tab over here, like simulation tab here. So we'll expose the parameter, say the width of overset. Okay, hit that. And then we'll create a bullet shape here using the oval method, creating an ellipse, yeah. So first we have to define the central point, the third point, and the second point. So we'll do it like this way. So there it is. Then we have to trim this, just like this and this. Oops, okay. Hit OK here. And create this line here. We'll trim it once again. Create this line here, trim, and there we go. Hit OK. Let's see if this works. Let's make it 20, right? There we go. The width increased, and the length increased accordingly. So that's what we want. So 15 is fine. Okay. And then we have to have a construction line to revolve this around. So instead of construction, rename this guy as overset sketch. All right. Revolve it. So it won't revolve because it will be choosing this construction line. So instead of choosing that, we'll choose line 6, which is the one over here. And we don't want it to be merging with the sphere, because we want it to have its own like body. So say OK. Oh, sorry, wait, we forgot to set the degree, the angle. So 360, hit OK, and there we go. This is our overset region. Now, what we have to do is subtract the sphere from the overset region. So first you select the overset region and subtract it from the sphere. Subtract the cape sphere from the overset region. Okay, you don't have to keep the tool body, just make it precise, hit OK. And there it is. Now let's rename it to overset region. Okay. So now let's select the faces for this guy. Deactivate the transparent scene thing. Rename it as overset surfaces. And then as a default, you have the surfaces of the sphere. So sphere surfaces. Save your CAD, and then let's go on with creating the domain. All right. So we'll create the domain by first creating a line here, and then making the length 0.6 meters, 60 centimeters. You have to optimize the distance between the inlet and the object, since the object will be applying pressure on the inlet up to a point. So for inlet not to be affected by this this phenomenon, this pressure thing, we have to make the inlet far enough from the object to have a good solution. So, okay. And then this side, the pressure output will be on here, and this will be 1.2 meters, okay? That's fine. And this will be how much? 0.75. So the total width will be 0.75 meters. So one is there, the other one should be here, which is 0. Okay. So you select this guy, the rectangle, and then you just create a rectangle here. Delete that, delete this, otherwise it won't be extruding. Oh, okay. Make these as construction lines, and you can actually expose the parameters of these guys. Like apply a length dimension, you can expose the parameter. But again, you can do this for parametric studies, but it's not in the scope of this tutorial. All right. So hit OK. And let's extrude this guy. First rename it to domain sketch and extrude it. And it must be symmetric. Both sides will be 0.35 meters. Okay, don't merge again, hit OK. So here's our air domain. Let's rename the surfaces. This will be the inlet. These guys, like hit Control, select all of these surfaces. Okay, select again. Okay, select these guys, select this guy. Right click, rename as pressure outlets. Okay, and as you can see here, we have the inlet, and then we have the pressure outlets. All 5 surfaces. Okay. Now let's create our, first rename this to air domain, or the background domain if you would like, anyway. XY plane, create sketch, normalize it, and then this volumetric mesh volume will be 0.25 in this direction. Right. And then in this direction, it will be 0.90, so 90 centimeters. And in this region, we will be acquiring data. So this is the fine mesh region where we will be exporting Excel folders, files. Okay, so, and the width will be 0.40 in total, 0.20 in this direction. Okay, and then 0.20 in this direction, 20. Hit this, delete this, delete that, set up constructions, right? Yeah. And then hit OK. And extrude this, and first rename it again. And this will be volume mesh sketch. Extrude it on extrude it symmetrically. We don't want it to be merging, two-way symmetric. And this will be around 0.25 in both directions. A bit smaller, let's do it like this way. Hit OK. And there we go. So we're pretty much done for the CAD. So okay. this as volumetric mesh, volume mesh, updated. All right, we're done with the CAD. Okay. Now, let's close the CAD. We're done with it. Now we're transferring the files, the parts to the simulation part of the tutorial. So right-click this guy, new geometry part. The tessellation, you want it to be very fine since it has small sections in the geometry. And tessellation is pretty much an initial mesh, let's say, mesh for the geometry. And you can see that once we say this, hide this body, hide the volumetric mesh as well. And you can see the tessellation now. Okay, hide. See the initial, it's pretty much like a surface mesh kind of thing. You can see the fine mesh. You can retessellate these as well, really. You can right-click, retessellate, and we can make it very coarse, for example. So, see the difference? So, but you would like a good tessellation. So, retessellate. Very fine. No, sorry, on the overset region. Retessellate. Very fine. So, yeah, much better. Okay. Right-click, restore all hidden parts. And they're all there. All right, hide the mesh. You can open and close the mesh here. Hide all the meshes or whatever, yeah. Now, save your simulation. So first, we need to create regions, 2 regions, one overset and one background region, or the main air domain on the back, yeah. So assign part to regions. So we chose 2 regions and we would like to create a region for each part and boundary for each part surface. Hit apply. And so before you create your own mesh, first define your boundaries. So make it velocity inlet, make this guy pressure outlet, okay? So we'll have like 5 pressure outlets, okay? And then the overset region, the overset surfaces will be overset. Where is it? Overset mesh. All right. Okay, so we can also create a physics continuum, select models. But before that, I always forget to do this. We have to create an interface between these 2 guys, okay? So select these 2 guys, create an interface, an overset mesh. And you can see the interaction between these 2, so they're both in purple. You can select an interpolation option, linear is fine, really, so we won't change that. For the physics, it will be 3-dimensional, it will be gas, coupled flow, and the constant density. We're subsonic, so there are no like huge density changes implicit on steady. It will be turbulent, yet it will automatically select Navier-Stokes, Reynolds average Navier-Stokes. We don't want that. We would like to select Large Eddy Simulation, okay? And we would like to select gravity for DFBI. So it's gravity and nothing else. That's all the models we will need. So there are a few things we can change here, but yeah, in the physics. So now here's the discretization thing. So upwind blending factor. So 0, as I told you, will be purely central, and you can actually change your discretization here. First order, second order, central, bounded central, and muscle third order. So the muscle third order option is great for, as I have read the articles, it's great for like coarse meshes. But our mesh will be pretty fine. So we can go with bounded central. Okay. And then since it's highly transient, the default factor was 0.15, so we'll make it 0.3. More towards the upwind discretization, just for the stability. All right. We won't change anything in the gas. For the gravity, always make sure the direction of the gravity, because it usually takes the gravity in the z direction. However, our gravity will be in the y-axis. So copy this, plug it here, and make this 0. Okay, so it's in the minus y direction. And we don't change anything else. Okay, let's get to the most crucial parameter, which is the meshing. So select these two, first remesher, trimmed prism layer. All right. So we have our measures, and base size will be 3 centimeters. All right. So instead of saying minimum surface size, so as I said, we have 2 millimeters thick cape, and we have to define a mesh size smaller than that. So we can make it 1 millimeter. Okay. And then surface curvature, since we have a lot of curved surfaces, we have to create a fine, define number of points in the circle to capture that curvature. So instead of like 36, we'll make it 108. So you can see the defined number of vertices on a curve with number of points. Or you can like make it better really, anyway. And surface growth rate will be slow. Number of prism layers will be 12. Prism layer stretching is 1.25, and this guy will be absolute, and this guy will be around 4 millimeters. So prism layer stretching is very important. So if you put a very small value to this guy, all of the prism layers will be accumulated on the surface of the boundary. Since it has to be at a specific thickness, it has to complete this thickness. So if you make the prism layer stretching value like really close to 1, then all the prism layers will be accumulating here, and the remaining prism layers, the last prism layers will be very thick. So you have to balance it out. So what prism layer stretching is, you start with the first prism layer near to the wall, and then the next prism layer will stretch in the factor of 1.25. So 1 millimeter times 1.25, not exactly in that order, but so it stretches the other prism layers according to the first prism layer. So it just stretches, gets bigger. So one of the good things about trimmer mesh is that you can actually control the transition between prism layer to the volumetric trimmer mesh. So we get here maximum core to prism transition ratio. So the prism layers are constructed. Then with this option enabled, it slowly transfers the prism layer mesh to the trimmer mesh. So it's a smoother transition between the surface mesh to the trimmer mesh, the volumetric mesh. So let's make it 7. The lower it is, the better, but to optimize between the number of cells, you'll increase it to 7. So now, volume growth rate will be slow. Okay, then the surface growth rate will be medium. The maximum cell size, so again, it's just volumetric growth rate. So smaller sections to bigger sections, either slow, fast, medium, whatever you would like. And maximum cell size. So if you're far away from the boundary, so let's say this is a huge domain, the algorithm will automatically apply the biggest cell size. So maximum cell size will be 3 meters, but we don't want it to be like that, say 100%, which is 3 centimeters. Okay. You don't want this. So the custom controls will have a volumetric control, and you have to choose your volumetric mesh. So this guy over here. Now, we would like to control surface remesher and the isotropic size of the trimmer, not the prism layers measures. The value will be absolute, and this will be 1.25 centimeters. Sorry, centimeters, okay? So that is it. And what else is there? Nothing else. Okay. So let's save this, our progress, let's save it. And so one last thing is the measure execution mode, make it parallel for faster generation. And also, since we have two different regions inside each other, we have to per part mesh. So it will mesh the overset region first, or the air domain, whatever the order is. And then, yeah, it will mesh these two parts separately. So let's execute. Okay, guys, my mesh is done, and we have to check this out, how the mesh ended up. So let's create a scene for that. So you can either create it from here, or, as I said from my previous videos, you can set it here, mesh. So it will show the surface mesh, but we would like to see the cross section, how it ended up. Well, in order to do that, we have to create derived parts. So right click, section, plane, and let's make this plane normal to Z and make this 0 right in the middle. Hit create, and then one plane normal to Y direction. Sorry, not X, Y. So again, right from the middle. Hit create. So we will have two plane sections. We can rename these as Z norm plane, and rename, copy, and this will be Y normal. So you can see from the axis which normal it is. Okay, so just add these two to the mesh existing displayer. Okay, and then go to, like, you can go to this tab for easier editing, and we can just deselect region. So now we can see the mesh. So the prism layer is pretty fine. There are some problematic meshes here, but really that's fine. It's not a huge problem. So let's see the quality of our cells. So in order to do that, right click, scalar, choose the same part. Oops, wrong one. So just choose the derived parts, and then say cell quality right there. So yeah, here, so cell quality 1 means pretty good. Again, there are some bad quality cells here, but yeah, that's fine, really. So we checked our mesh. We will use the scene later on, so don't delete it. Let's go back. So the next thing is, let's create our motion, all right? And you can do that by going to the Tools tab, right at the end of all of these tabs, and then you go to Motions right here. Right click it, say DFBI Rotation and Translation. So we have created it, and it will create a tab here. No, not now, because we have to choose it. So our overset region will be moving, and we have to choose this as not this one. The motion under physics values, under regions, we'll make it DFBI rotation, and we'll have a DFBI tab here. Now, new body, 3D continuum body, or you can create a mechanical body, like a solid body, but here we'll just create a continuum body. We'll select this, and say sphere surfaces. And it will really move in the Z, it will really rotate in the Z axis. So just enable this Z rotation. It won't translate. You can also, I mean, it will have drag forces, right? You can also select X translation, but it's not in the scope of this work. And the initial values. And this will be the center of mass, moment of inertia, and all of these, also the body mass, will figure those values out from extracting these spheres, the Cape spheres, CAD to Inventor or some other software in which we can change the material. So what we have to do is that go here, roll back. And then, no, roll forward to like Fillet 2. And then go here, export. And then you can rename it as anything you would like. I have renamed mine Cape Sphere Trial 2. I can just save it. Let's hit yes. Then open up your inventor and then say open. Hopefully it will open. Okay. So you have to choose, you can choose all files. It will show all of the files. I don't want that. Just show the XP ones. And then choose this guy. And it will take a while for it to open. Okay. Everything is fine. Hit OK. Okay. All right. So first thing we would like to do is manage. So it will, we want the values to be in SI values. So what we have to do is go to Tools, Document Settings, Unit. Instead of this, we would like kilograms. Hit apply. And so first, select your material, which will be rubber, right there. Okay, changed color. Then you go here, I properties, physical, very high, say update. So you get the center of gravity, you get your mass, you get your principal moments and whatnot, right? So let's go back to our simulation, close the 3D CAD. But before that, this will give you an error. Roll to the end, update. You have to mesh again. I'll mesh it now. Okay. So we can plug in the value. Our mass was 0.563 kilograms. The release time means when the motion should start. So you can start the motion after 1 second when the when the flow is steady. Okay, but our flow will never be steady, so we don't put a release time in this. Ramp time is the ramping up forces between release time, so it just ramps up the forces slowly. And we have two external forces. One is gravity, one is fluid force, okay? So free motion, you can change this. You have a variety of choices here, okay? So anyway, so we just changed the mass. Center of mass was 0.3 meters away, right? Let's check it out again. Yes, and then go back. Moment of inertia in the X 0, 0, 1, and then Y 0, 5, and then here this. So the principal, these ones are not changing, they're just 0. Okay. Right. I mean, you can create your own orientation, angular velocity you can give. I mean, for example, you can just give a 1 radians per second, or it doesn't matter, or just leave it, it's fine. So everything is fine here. We don't have constraints, we don't have body couplings. if you have several mechanical bodies, then you can set constraints, couple these two together, and you have several options: spring, contact, spherical joint, and all those. And yeah, so that is done. And finally, we have to optimize our solvers, okay? And so the maximum velocity of the flow will be around 37 meters per second. So if we want a current number under 1, we have to calculate this. Okay, let's calculate. So we want, so the current is, so how do you calculate current number? Is through, let me show you. So yeah, so how you calculate this is that CFL equals to your velocity times your time step divided by your mesh size, right? So let's determine this. So our mesh size around our finest mesh size is the prism layer, but I'll just take 1.25 centimeter as our reference. Okay, so CFL has to be around 1 times, so your mesh size 0.0125. Okay, and then let's divide our, so these should be in SI units, okay, so it has to be in meters. So let's divide our velocity by 37 or 40, okay, you can make an estimation, that's fine. So our time step should be around 3 times 10 to the power of -4. However, we have prism layers, right? It would be a better idea if you make this smaller. So after my trial and error, like I have ran this simulation several times, I have found it to be better with 5e minus 5, meaning 10 to the power of -5. And let's make it second order. And this is the temporal discretization, which you can give accurate results. But again, the higher order discretization you have, the more unstable it gets. Always keep this in mind. So the constant CFL will be 0.2, and our high accuracy temporal discretization, the option we chose here, will be fourth order, not fifth. It's more unstable, okay? So the other thing we have to do is that we would like to store the calculations made by the coupled solver, okay? Such as the gradients, the pressure gradients, and whatnot, and the corrections and all that. So let's click that. Also by the Veil HGS viscosity, okay? So the final thing is inlet boundary condition, since we'll give it a sine wave, okay? So let's go down to tools, field functions, new, will be a scalar function. Let's make it velocity inlet profile, right? And copy this name to function name. Okay, it will be dimensionless. So it will be length. Yeah, it's pretty much velocity. But 0, velocity, give it 1. And yeah. The definition will be, so we can just copy and paste it. I'll give this in the description below, or you can just write the same thing. But first, we have to create our initial boundary and velocity. So this is a parameter I have given. Okay, first let's just copy and paste this, just for an ease for me. Okay. So we're missing this guy. Okay. And this was from my previous simulation. And we have to create a parameter first. So let's create it. Chill boundary velocity. So the parameters are here, right? New scalar. And we'll say this IT/BC velocity. Okay. This will be not dimensionless. It will have the dimensions of velocity again. And we'll give this a 10. Okay, so let's go back to our field function. And we have to change this to exactly the name of this guy, ITBC. You can just write that. So, okay, just switch this IT, this guy, and then IT, this guy. So this is the time. So it propagates through the time, and then we have the initial velocity, which starts from 10. So it's purely for that. But we'll start from 10, go in the Fourier series manner. So we can actually preview, and our dependent variable will be time. So let's make this larger. Okay. So the range will be, let's make it 2, and our IT will be 10. Okay, so it starts from 10, approximately around 10, and the range is around 2, or we can make it 1. So here's our profile, so it's around, yeah. So it drops down, goes up, drops down further, yeah. You can play with these as well, your choice. Okay, so we can make the parameter 5 as well. Just reduce this, and yeah, okay, 10, hit okay. So what we have to do now is that go to our boundaries, velocity inlet, and make this a field function and velocity. So here's our velocity inlet profile. Hit that. So yeah, pretty much it's over there. And yeah. So now you can actually just run the simulation. But first, I forgot to initialize. Our initial velocity will be a composite, and we only want the initial velocity to be in the x direction. So what we have to do is that make it 0, so IT VC velocity. So the parameter we have set here. So why do we create a parameter? Because so we can change the value in the field function we have written for the velocity inlet and the initial condition just by one parameter, just by coming here and then changing this to 5, right, or 10, whatever. So yeah. So that's done. So we have given a constant. So these are 0, and that is it. So you guys, you can just pretty much just initialize your simulation here, and it will just automatically run. Okay. However, we have to change the solvers. So we have changed that. We have changed the constant CFL, which is around 0.2. And we also have to change this maximum inner iterations. And I have found it to be 15 is the ideal number. If it's 20, it's a lot better. So 2 seconds maybe, or 1 second is enough. And yeah. Oh, also disable this. So after 1,000 steps, it will automatically stop. So we don't want that. So also, the final thing is just activate autosave, okay, and say that for every time step, make it 150 iterations, every 150 time steps. Because later on, we'll be continuing this simulation and we'll be collecting data in sliding sample windows, right? And it takes a lot of hard disk storage, for example, like around 30 gigabytes. So we don't want to save like so frequently. So we'll just save it in intervals. Okay, you can just run your simulation and let's see if the our initial condition worked, and we can see that through these two. Okay, scalar, go to the scene like this over here, say velocity, and then velocity magnitude pretty much. So it's 10 everywhere. And if we say velocity I, so again, it's I, like it's just 10 everywhere again. We say J should be 0, so it's right. So, okay. So this is it, you guys. This is the part 1 of the video. I'll make either one more part or 2 more parts, so it will have 3 parts in total, including this one. So thank you for watching, and I'll see you next time. And I'll continue with the second part as soon as possible. So thank you for watching. Have a nice day.